I'm starting the recording also.
Okay, sure. Yeah, so before I start today's topic, let me know if you have any query from yesterday's class. Okay. So if not, then let me start with today's topic. So today we are going to look into the consensus protocol in the permission blockchain model. So till now, what we have seen that, well, this basic idea behind this blockchain that was developed for using in cryptocurrency environment was to have a kind of completely open chain. That means an open network of participants where any participant can join or leave or can initiate a transactions or can just join to observe what is going on in the network. And for that kind of architecture, we have seen that we can use algorithms or method like proof of work or Nakamoto consensus to achieve the consensus on the newly proposed block. Although we have seen that this Nakamoto consensus or proof of work, it provides priority to liveness over safety, and because of which we have possibility of having a fork, and that way we cannot support consensus finality immediately. But it's a kind of workaround solution that works good for cryptocurrencies, and that can provide a viable setting of utilizing cryptocurrencies. And the way Satoshi designed that entire idea of Bitcoin, he or she introduced this concept of economic models along with the consensus, where this consensus is not only committing a new block, but also generating a reward which will be given to the miner. And that way it will encourage participants to join as a miner to mining new block in a complete decentralized way. And that way he or she made the architecture kind of interesting and secured against any kind of external attack. Although theoretically attacks are possible, but as you have seen that in practice, there was very less instances of attacks which were successful on top of the Bitcoin network. And once the Bitcoin network has grown significantly large, we do not see any kind of such attack instances on the Bitcoin network, particularly because it has now become a kind of truly decentralized system. Now with this, what we have also seen that this proof of work or the Nakamoto consensus, it has a major limitation in terms of transaction throughput and the corresponding power consumption. So what we have seen that, well, this proof of work mechanism, the way it works, it consumes a hell lot of power, and that amount of power consumption is significantly high and generate a huge amount of carbon footprint. So that is one of the major disadvantage of such kind of protocols. On the other hand, we have seen that the transaction throughput for such kind of architecture is also very low. So you can commit a new block in around 10 minutes, and as a result that you can have around 3.3 to 5 transactions per second that can be committed in a block. Now with this particular architecture, the major problem that is there is that whether such kind of, or although such kind of consensus algorithm is suitable for cryptocurrency kind of applications, but if we try to find out the application of blockchain beyond cryptocurrency, we'll see that this kind of proof of work consensus mechanism is not very suitable for such kind of architecture. So for example, if you look into the enterprise setup where you need to kind of make a coordination among different stakeholders which are otherwise competitor to each other in the business, but still we can apply some kind of blockchain-based platform to have a kind of transparent way of communicating among themselves. But for such kind of architecture, this proof of work is not a suitable mechanism, because people will not be agree to spend that much of power, and at the same time they will not agree to work on such kind of low throughput or low transaction throughput based system. So that was the major limitation that we have seen in proof of work based consensus mechanism in a permissionless model. Now whenever we are moving towards this permissionless model to permission model, one primary observation that we have that the enterprise networks, they are actually not a truly open network. Rather, there are fixed number of participants who are participating in the business, and they have kind of a kind of authenticated and authorized network. Well, so this permission model, what it says that, well, you can use the blockchain architecture where the users are authenticated a priori, authenticated and authorized a priori. That means you have a membership service provider or MSP, which can help the participants to obtain the membership in a blockchain or in a blockchain network. And that way, after getting authenticated in a blockchain network, the participants can join in the network. So that way, because the participants are pre-authenticated and pre-authorized, these participants, they know each other. Well, but the interesting fact here is that the participants may not trust each other. So although I know you, but I do not trust you because we are the business competitors. Well, so such kind of model is there. So that is the reason if I want to share certain information among ourselves, we cannot directly share it because there is such kind of trust issues. And as a result, blockchain can be a very interesting solution for such kind of problem. Okay, so the idea was that, well, you run blockchain among known and identified participants. So let me give you one practical example. So that is actually one of the projects that had been taken by the Singapore government, and that particular project was led by IBM Research, IBM Blockchain Innovation Lab at Singapore. So I got a demonstration of that project during my visit at IBM Singapore lab. So the problem with this country, Singapore, is that you know that it is a very small country, right? And as such, they do not produce much food items like the vegetables, the general crops, and so on. So they do not have a lot of field from where they can grow the crops and they can still satisfy the need of the people of that country. So as a result, what they do that they import majority of those vegetables. Well, so they typically import the vegetables from various neighboring countries like say Myanmar, then Vietnam, so all these, then Malaysia, all these neighboring countries. And as a result, what they do, so Singapore has a kind of very large shipping industry, and at the same time they have a good base in fishing. So that means the fishes which are being caught from the seas. So what they do that they basically import these vegetable items from the neighboring countries and they export fish to those countries. So to maintain this particular business, what they did, they actually made a contract with Walmart. So you know that Walmart is a giant name in such kind of import-export business or cross-border trading. So they relied on Walmart, and what the government told to Walmart that depending on the demand and supply, what you do that you export the fishes from Singapore to the neighboring countries and you import the vegetables in time. Now, what Walmart did, Walmart relied on multiple small shipping companies which are there in and around Singapore. So they relied on those shipping companies and they instructed the shipping companies that, well, depending on this demand and supply, what you do that you pick up the fish from Singapore, deliver it to say in Malaysia, and then pick up the vegetable from Malaysia and deliver it to Singapore. So that way, you can minimize your transport cost, and at the same time, you can actually have a kind of efficient supply chain in the entire procedure. But in practice, what happened that these individual shipping companies, they were not coordinating with each other, and as a result, what happened that the shipping companies, they used to send empty ships to Malaysia to pick up the vegetables from there. And whenever they were exporting the fishes from Singapore to Malaysia, they have taken the fishes to Malaysia and then returned back with empty ships. So that way, this transport cost becomes twice. Well, so at that time, initially, Singapore government thought of that, well, let us digitize this entire platform. and try to gather as many information as we can. But then comes the problem that who is going to digitize this entire business model, and who is going to make it mandate that you need to come to this common digital platform, because everyone is a kind of competitor to each other. So all the shipping companies, they are competitor to each other. Then they are relying on Walmart, but at the same time they have their other businesses apart from the contract with Walmart. Well, and then the government, which is actually play a kind of coordination, trying to play a coordination role among them, but the government do not have a kind of proper information that which ships are at what place. So initially they have tried to build up a kind of centralized digital platform, but the problem with that centralized digital platform is that the shipping companies are not very willing to join in that digital platform. Well, so primarily because they said that, well, this particular digital platform, it is not secured, and I am providing, so the government thought of to put the sensors on the ship so that they can monitor that what is the quality, means what is the quality of the food item, what that is being transported. But then the shipping company put an objection that you are putting the sensors in my ship. That means you will not only sensing the data that is during the time when I'm involved in your business, but you are also sensing the data from my other business. Now, what happens if the data gets leaked? Then my business data gets leaked, and the other people or the other participants, they will, my competitors will get my business data. Well, so that way the coordination problem was there, that who is going to maintain the data, where the data is going to be stored, who is going to own the data, who will decide that what part of data to share with whom. And ultimately, they came up with a blockchain-based solution. So that blockchain-based solution was actually designed by IBM Blockchain Innovation Lab at Singapore. So they actually put up all these individual stakeholders in a common blockchain platform. Well, and that common blockchain platform, it actually had later on, whenever we are going to learn about this concept of Hyperledger Fabric. So this entire platform was actually implemented with the help of Hyperledger Fabric, and you will see that Hyperledger Fabric has another nice concept called channel. So you can actually use this concept of channel to share your data in a kind of privacy preserved way. That means you can decide that which part of your data will be accessible to whom. Well, so that kind of architecture, blockchain-based architecture, was used here. Now, why I was trying to tell you this entire story, because here you see that there is a need for such kind of decentralized solution, because you have multiple stakeholders, you have multiple shipping companies, and these shipping companies are involved in multiple different businesses, and they do not want that their business secret gets revealed. But at the same time, if you can share certain portion of the data, then the entire business model gets improved a lot. So you can actually maintain the quality of delivery during the supply chain. The government can minimize its cost of importing the items, and it can actually export the items to the proper location where the demand is more, or from where they can get kind of maximum profit. Well, so that way you can do a kind of interesting and kind of more optimized planning of your supply chain. Now, here you see that in this architecture, if I say that I'm going to use a proof of work type of consensus mechanism, then proof of work type of consensus mechanism is not going to be viable here. Well, but remember always that I can always use proof of work type mechanism here in this architecture as well. But it is not cost effective, because say here you have some handful, means although you have multiple stakeholders, multiple different shipping organizations, but you have a fixed number of shipping organizations. So you have some 30, 40 different shipping organizations. It is not like that you have millions of shipping organizations. Well, now whenever you have 30, 40 such nodes in your peer, first of all, your network is not sufficiently large enough. And when your network is not sufficiently large enough, again, you cannot ensure or you cannot guarantee that the general security primitives which are being supported by this proof of work consensus, that will be guaranteed here as well. Because as I was mentioning multiple times, that the basic primitive behind the security of proof of work is that you are using a kind of large network which is truly decentralized. attackers will not be able to gain control over more than 50% of the mining power of the network. Well, so that is one of the prime requirement. But when your network is small, you cannot guarantee that. But if you look into the data structure perspective, that means the basic blockchain architectural perspective, you will see that, well, blockchain plays a pivotal role here. And if you can use blockchain, you can actually solve this particular problem. Well, so blockchain can be a kind of very useful solution in this context. Now here, what happens that we can understand that we still have a need to run a blockchain service among these peers. But the problem is that I cannot use proof of work type of consensus to reach into the consensus of this entire network. Well, so from here, people started to think about that, well, how I can still be able to run blockchain in such kind of enterprise setup without having that significant amount of mining cost and as well as the low transaction throughput. So I need to basically reinvent, or I need to rethink about the underlying consensus mechanism which is running in blockchain. So as I was mentioning, so this is the kind of use case for such kind of model, that this kind of permission models are particularly interesting for the business applications. And here actually you can see that you can interestingly execute the smart contracts among a closed set of participants. So here in the example that I have given, among all those shipping organizations, you can run multiple smart contracts to automatically schedule the supply chain or to automatically schedule the transport depending on the demand and supply at different location. Well, and depending on the current location of a ship, you can redirect it. You can decide, depending on the quality of the food item, you can decide that, well, whether the ship wants to go to that port which is far from its current location, or whether it need to deliver the goods to a port which is near to it. Well, so that way you can run multiple different smart contracts to make such kind of decision. Well, and you can do a provenance tracking of the assets on a supply chain. So this is a kind of interesting use case for permission model. Now the question comes that how do we execute smart contracts over such kind of closed network? Well, so the idea of smart contract we have discussed earlier in brief, but in summary, what a smart contract is, basically a smart contract is a self-executing contract in which the terms of the agreement between the buyer and the seller is directly written into the lines of code. Well, so that means you are representing the contract in the form of an executable program, and you are facilitating a decentralized execution of the contract on your entire platform. Well, so that is the kind of purpose of a smart contract. So to come to an agreement on a smart contract execution, what typically you have to do? So these are the kind of steps for my smart contract execution, that you design the contract offline, you design the contract off chain, and then store the contract on a blockchain. So whenever you are storing the contract on a blockchain, all the peers or all the participants can see that contract, and they can actually find out that how to execute the contract. Now, once certain event is triggered, that means you need to execute certain part of the contract. So you execute the codes locally on each peer. Well, now, once you have executed that transactions on each peer, then you generate the transactions as the output of the contract execution. So that particular contract execution has generated certain output. So that output, you initiate it as a kind of transactions on top of blockchain, so that you ensure that the output where you have reached, it is agreed upon all the participants in the network. Okay. Now, the peers of the blockchain network, they validate the transaction, and the output is committed in the blockchain. So whenever you are committing the output in the blockchain, that may again trigger the next event, which can execute the next code, or which can generate the next transaction from the smart contract. So that way the smart contracts keep on executing. So you look into for certain kind of event which has been occurred. Depending on that event, you start executing the smart contract. Once your execution is over, you have reached to some output state, then you broadcast that output state as a transaction on the blockchain. So let other participants, they also validate the output, and they agree on that particular output from the smart contract. And then that output is committed in the blockchain itself. So that way you ensure that all the participants are actually agreeing on the correct output of the smart contract. Well, so and that way you are facilitating the decentralized execution of the smart contract, which can help in supporting your business logic in a complete decentralized environment. But the interesting fact or the interesting aspect here is that in the second step of the smart contract execution, what I'm saying that once the event is triggered, then you execute the codes locally on each peer. Well, so the question comes that do we really need to execute the code on each peer? Or what I can assume that, well, a subset of that peers is going to execute the code, and then we are having certain kind of consensus mechanism which will ensure that majority of the participants or majority of the peers in the network are agreeing on the output of that particular contract. Okay, so that way we can design the entire architecture keeping in mind of this particular question. Well, and a related question which comes that when does each peer execute the code? So whenever I'm saying that, well, multiple peers can execute the code, and remember that we are again talking about a distributed system. Well, so earlier we have mentioned that Professor Sural also mentioned that in a complete distributed system, you will never be able to ensure clock synchronization or a perfect clock synchronization. You can use protocols like NTP, but still you have certain amount of drift. And at the same time, whenever you are sending certain message over the internet, you actually do not have any control over how much time it will take to reach that message to your destination. Well, so that way our network typically behave like an asynchronous network. And the question comes that in an asynchronous network, how will you ensure a synchronization among the peers in terms of executing the code? So it might happen that one peer, it got the event right now and it has started executing the code. And finally, once the code execution is over, it is going to generate the transaction. And another peer, for it, it has not yet started executing the contract. It is waiting for the event. Maybe the event will appear after some 10 minutes, and after 10 minutes, that participant or that node will start executing the contract. So that way, this contract execution is asynchronous, but at the same time, I need to ensure that majority of the participants in the network, they agree on the common output of the contract. Okay, so that is the kind of requirement that I have whenever I am executing a smart contract on a decentralized platform. So what we can do, or what people have done, they have tried to visualize a smart contract agreement as a state machine replication. So if you have done a course on distributed system, you already know what is state machine replication and the different kind of algorithms which are being used in the literature in the classical distributed system work to ensure this state machine replication or to provide to support test machine state machine replication. So what is the core idea here? So the core idea here is that you execute the contract on a subset of nodes and ensure that the same state is propagated to all other nodes. Well, so that means although a part of the network is executing the contract at the current instance and they may not be synchronized, but whenever they are generating the output of the contract, that output of the contract gets validated across multiple peers. Well, and that contract actually ensure, or execution of that contract ensure that you are validating the correct output of the contract. Okay, so that means this validation means that majority of the peers should agree on the state. Well, now to do this validation, what you can do, that you can generate a proof that a peer has agreed on the state of execution, and later on we'll see that how you are going to generate this proof. Okay, so we'll see that we are going to use ideas like collective signatures or COSI to actually generate such kind of proof, which actually ensures that, well, majority of the participants have agreed on this state of execution of the smart contract, and they can ensure that the contract have been executed correctly on the decentralized architecture. Well, now, question comes that how will we generate the proof? Well, so the problem that I have just mentioned, that well, you can say that well, I will attach a proof which will validate the state of execution of a smart contract, but again the problem comes that how will you generate such kind of proof? Now to generate the proof, we rely on state machine replication algorithm from the classical distributed system consensus. What the state machine replication says, it says that you can represent the smart contract as a state machine. Well, now here you actually need a little bit of your knowledge on fundamentals of computer science. So I guess that all of you know, or all of you will agree that any deterministically executable code, we can represent it in the form of a state machine. Okay? So I guess that you remember that idea of Mealy machine and Moore machine that you have learned in your theory of computation course. And this Mealy machine or Moore machine, they are nothing but different kind of representation of an program which can get executed and which can produce deterministic result, right? So that way, any deterministically executable code or any algorithm can be represented in the form of a state machine. Right? So here is an example. So I have written a piece of code here that I am at state S1. Under that, I'm doing that while I have more amount of goods. That means more goods equal to 1. I will keep on delivering the goods. While more goods becomes 0, that means I am done with delivering the goods. There are no more goods. I come to the state S2 and I check another variable that whether all order are complete. Well, so if all order are complete, then again I go to the state 1. Otherwise, I print that well, goods transfer is complete. Well, so all order complete equal to 0 means the orders are not complete yet. So I have pending orders that need to be fulfilled. Now, if I try to generate a state machine for this piece of code, you can see that I can have it something like this automaton, where I am at state S1. From state S1, whenever I am getting an input 1, I am remaining in that state. Well, and I'm keeping on delivering the goods. So once I'm getting an input as 0, that means my more goods become 0. I move from S1 to S2. Now at S2, again, I am looking for whether all orders are complete or not. If all orders are not complete, that means if all orders complete equal to 0, then I move to the states S1 again to deliver the goods corresponds to that contract. Otherwise, I say that all the transfers are complete and I move to state S3, that is the final state. So that way, the kind of smart contracts or any kind of executable code, we can represent it in the form of a state machine. Well, now in a distributed architecture, let us see that how this state machine replication mechanism works. Well, so again, I'm saying that this may be some kind of repetition, or the people who have already taken a course on distributed system, you may know this, the idea of the state machine replication and the different kind of protocols which are being generated for achieving consensus during state machine replication. But I'm just trying to explain that things from the concept, from the perspective of a blockchain. So let me know that if you have any query or question up to this point. Otherwise, I will move to this explanation of this state machine replication mechanism. Any query? Okay. So how this state machine replication works? So the state machine replication here, the finite state machine that you have. So this finite state machine is the representation of your executable code. That means the smart contract. So this finite state machine, it is replicated over all other independent servers that you have. Well, so the state machine is actually been replicated over multiple different servers, and these servers agree on this particular state machine. Now the clients keep on generating the transactions. Say here is one client who is generating a transaction saying that, hey, I have delivered 100 kg of potato. And then there can be another transaction T2, which is saying that, hey, I have delivered 50 kg of tomatoes. Now here one interesting point that you can see that these transactions are not coming to a single node all the time. Okay, because you remember that I'm utilizing a kind of decentralized architecture. So for example, if I'm having in that Singapore government example, if I'm having if I'm a shipping company, then I will maintain my own server. Now, when my clients are completing their good delivery, they are informing me. Similarly, for your shipping company, you are maintaining your own server, and that way, whenever your client are completing the delivery, you are getting those messages. Right. Now, the question here is that I need to make a coordination among all these different instances. So, different servers are getting different instances of T1 and T2, different instances of these transactions. Now, what I have to do that I need to come to a consensus on the ordering of the transaction. So, this ordering of the transaction is very much important. Well, because you see that the output many of the times it depends on in which order you are executing the transactions. Well, so later on we'll see that in the context of a smart contract, how do we execute different type of transactions or a set of transactions while maintaining the order of execution for the blockchain. Whenever you are having multiple transactions and you want to get those transactions executed, you need to execute those transactions in a particular order. Well, so that is again coming from your algorithmic concept or the concepts of your theory of computation. So if you change this ordering of the transactions, you might result in a different output. That might also happen. So that way you have certain kind of ordering logic. And depending on that ordering logic, what you can do that you can actually define the ordering of this transaction. But as different participants have got different transactions and they are doing this ordering of the transactions in a complete decentralized way, that way I need to have a kind of consensus among the participants in terms of ordering of the transaction. Now, how do we do that? We run some kind of consensus algorithm here. Later on, we'll see that what kind of consensus algorithms we can execute in this context. So we can run this consensus algorithm and we can make sure that all the participating nodes, they agree on a common ordering of the transaction. So they agree that, well, first T1 will be executed, then T2 will be executed. Now, once you have reached to a ordering, then the next task comes to start executing the transactions. Okay. So what you do that every individual machine, they will independently start this execution. Well, so you first execute T1. So from S1, from your current state S1, you execute T1. Say after executing T2, you have reached to state S2. And at this state, you decide or you see that, well, the execution of the transaction 1 is complete. So you see that whether you have more orders, that means whether T2 is non-zero. If T2 is non-zero, that basically means I need to now execute T2 again on top of the output that I have got from T1. So you execute T2 on state S2, and accordingly you decide your final state after executing both T1 and T2. Okay. So once this execution is over in a particular order, then the nodes, they reach to a final state. So here after completing the execution, we see that all of the state machines, they have reached to state S1. Now, whenever they have reached to state S1 at this point of time, again, I have to run another set of consensus. So why do I need to run this set of consensus? I need to run this set of consensus to ensure that all the participating nodes have committed, or all the participating nodes have reached at state S1 after completing the execution of the transactions in order. Now, once that is done, once they are agreeing on that output of the transaction, then again the individual servers can keep on informing their clients about the current market situation. Now, here is an interesting fact. What is this interesting fact? Here you see that this right-hand side server, it is informing the stakeholder that, well, what is the output after executing T1 and T2. But it might happen that this particular node is an attacker. Well, so that is a malicious node. Now, if the client gets the information from this malicious node, that means whatever information the client is getting, that is wrong. Well, now you can say that during majority voting, what I can do that during majority voting, I can find out that, well, which particular state has been agreed by majority of the servers, and you can agree on that state. But again, the problem here is that this particular node is the attacker itself. So for the set of clients which are connected to this particular node, they are surely or they are likely to get suffered. Okay, because they are going to get the wrong information. So maybe this client is saying that you have reached state S3, whereas in practice it is not in state S3, rather it is in state S1. So this is the kind of problem that I have. So what we see that there is a natural reason to use this state machine replication based consensus over permission blockchain model, primarily because first of all the network is closed, the nodes, they know each other well, so you can use such kind of state replication. But on the other hand, we also land up into multiple issues. Okay, so here what we see that we have advantage in terms of that the network is closed. Because the network is closed, the nodes know each other. Because the nodes know each other, so state replication is possible among the known nodes. This way, you can also avoid the overhead of mining. So remember that the state machine replication, that is a kind of message passing based system. Well, so once you have reached to a particular state, you need to inform that state to other participants. So that way you can avoid the overhead of mining. However, you still need the consensus, okay? Because certain machines, those machines can be faulty or those machines can behave maliciously. Okay, so the machines can be faulty or the machines can be behave maliciously, and because of that reason, you still need consensus. So that way, we need a bit of redesign on the state machine replication, the core idea of the state machine replication. Well, so the core idea that is being used here to apply for state machine replication is that along with this classical distributed consensus algorithm, you bring up the idea of cryptography and digital signature, and then you combine crypto and classical distributed consensus together to design or to think of the consensus for the permission blockchain. Okay, and as a consequence, you will see that this classical distributed consensus algorithms like Paxos, Raft, Byzantine fault tolerant algorithms, etc., which are state machine replication mechanism. With that algorithm, we can utilize that algorithm along with the necessary cryptographic tool to support consensus on case of a permission blockchain. Well, so that way we are going to revisit this set of consensus algorithms, and we are going to see that how these consensus algorithms can be applied in an interesting way on designing the consensus mechanism for a permission blockchain model. Well, so overall, what we have seen till now that this set of algorithms or this consensus mechanism which is required for a permission blockchain model, that is a bit different from the requirement that we had in case of permissionless model. In case of permissionless model, because we are having an open environment and we had the challenge of open environment, we have used this approaches like proof of work, which is not very environment friendly and which is not energy friendly. But whenever we are thinking of, or whether we are thinking of a use case where we can apply the idea of blockchain in a kind of closed network, in a permission network, then we can reutilize or revisit this idea of state machine replication and the consensus algorithms that were built on top of state machine replication to support the operations of blockchain in a closed community as well. Well, so any query or any question up to this point? Okay. So if there are no questions, so for today's class, we are stopping a bit early, but let me stop here. This Paxos raft, they need a kind of good foundational discussion. So we'll start it in the coming week, the discussion on that different kind of distributed consensus algorithms and how they are applicable for a blockchain-based system. Tomorrow we are going to have the test during the class hours. So please be available at 9 for the test. During that class hour itself, we'll let you know the modalities and everything that you have to follow for the test. Okay, so if you do not have any query, then let me stop here today.